新宿です。The next station is 新宿。The next station is Shinjuku. The doors on the right side will open. Please change it for the Yamaguchi Line, the Chuo Line, the Odakun Line, the Keio Line, the Marunoki Subway Line, the Shinjuku Subway Line, and the Oedo Subway Line.
新宿です。お出口は右側です。お降りのお客様はお忘れはなさいませんようお気をつけください。新宿です。お忘れ物ないようお気をつけください。このバスは臨海線特急新木場駅で渋谷駅と先の中小の大崎から臨海線に行きます。横浜方面には行きません。横浜方面湘南新宿線この電車の中で乗ります。乗りましたものでお待ちください。
最初は朝から新橋駅を発車いたします。
1番線ドアが閉まります。ご注意ください。この電車は臨海線特急各駅停車新木場行きです。次は渋谷です。 This is a Lincoln Line train for Shinkiba. The next station is Shibuya.
The next station is Shibuya. The doors on the right side will open. Please change it for the Tokyu Toyoko Line, the Tokyu Dei-Toshi Line, the Keio Inokashira Line, the Ginza Subway Line, the Hansoma Subway Line, and the Suikoshi Subway Line.
As a matter of convention, whether we refer to it as a distinct row object or a column object. And we also know that the zeros at the end are kind of optional. We can also think about representing this by including a 0 here, representing that there's 0, 4 singletons, maybe another 0 representing 0, 5 singletons, and so on. So you can see now there's an obvious connection between this and the polynumber story. A polynumber was essentially just exactly like this. So there must be some connection, there's obviously a connection between polynumbers and vectors. And that's interesting, I think, for us. And we'll just point out that vectors, because they're multi-sets, they can be added. You can add A to multi-sets, just put them all together. So if D and W are vectors, then we can form D plus W. We can multiply D by 2. We take a linear combination like 3D plus 4W. These are all easily defined because D and W are vectors, they're multi-sets. So we gain a lot of infrastructure for free by having our objects be multi-sets. This is a kind of theme that's underlying a lot of what I've been doing and will be doing in the last few presentations. So now we want to move towards bringing the third kind of object that we're interested in, which are Hindu-Arabic numbers. And we want to kind of bring all these three things together into the same pot. The polynumbers, vectors, and Hindu-Arabic numbers. So it turns out that because the same objects are good for describing any three of those things, natural synergy between these three things. So to move in that direction, we need to talk about how we're going to multiply vectors. And we're going to start doing that by explaining how to multiply singletons. Because vectors are m sets of singletons, if we know how to multiply singletons, hey, we know how to multiply m sets of them automatically. Because we know how to multiply vectors. So the definition of the multiplication of singleton is rather surprising, perhaps, at least if you don't know where we're headed towards. Okay, so we have two singletons here. The singleton n, the singleton m. N and m are necessarily natural numbers. 0, 1, 2, 3, 4, etc. Two of those things. And we're going to define the product of the singleton n times the singleton m to be the singleton n plus m, where this is just the usual addition of natural numbers. This is a surprising definition. We're defining a multiplication in terms of an underlying addition. I think it reminds us perhaps a little bit about the tropical calculus, doesn't it? I kind of think what's going on there too. Vectors is now straightforward. So here's a vector V, here's another vector W, we need to multiply them. The product is going to be defined in terms of the underlying products of the singletons contained in there. And we know that that product is determined essentially by the addition of the numbers inside the singletons. So when we multiply this singleton by this singleton, 0 times 1, the singleton 0 times the singleton 1, we get the singleton 1, 0 plus 1, 1. And so this times this one is this times this is this, and this times this is that, this times this is that, this times this is that, and this 2 times that 1 is another 3, 2 times 3, that will be a 5, 2 times 3 is a 5 there. So if 2 times 3 is 5, I don't really mean the number 2 times the number 3 is 5, the number 5, I rather mean the singleton 2 times the singleton 3 is the singleton 5. Okay, and we can represent this by thinking about the corresponding pictures, descriptions of these vectors in terms of row or column 3 type vectors. So this one here, that special, is described by 2, 0, 1. There's 2 zeros, 0, 1, and 1, 2. This one here is described by 0, 1, 0, 2. There's 0 zeros, 1, 1, 0, 2s, and 2 3s. And this one here is conjunction here. And then if you think about it for a while, you can convince yourself that this product here is in fact exactly the same as polynumber multiplication. Even if they look like polynumbers, instead of a green border here, instead of a flat up on top. But otherwise they're just the same. And you can check that this is exactly the same as corresponding polynumber multiplication. So this is another way of thinking about polynumber multiplication. It's really generated by this very simple multiplication of singletons. So there's that one equation involved. Okay, so we've seen that there's a very close connection between vectors and polynumbers. They're almost the same thing. And here are some of the laws for arithmetic vectors that we can easily deduce from our definitions. And in fact, these laws are almost automatic now. There's not any serious difficulty in seeing why they're true. So if V, W, and U are vectors, if N and M happen to be natural numbers, then we have commutativity of addition and associativity of addition, because the addition of vectors is basically just N set addition, and we know that's really different. We know that we can multiply say some equals W by some natural number N, and that's the same as N times V equals N times W. With regard to our multiplication, well, the commutativity and the associativity of the multiplication follows immediately from the commutativity and associativity of the multiplication at the singleton level, which is a consequence of the commutativity and associativity for natural number addition. We have some other laws having to do with how numbers multiply vectors, which are pretty straightforward. We have important distributive laws. These, again, are just natural consequences of the fact that we defined our multiplication in an M-set kind of way, multi-set orientation, depending on an interior multiplication of elements. So whenever you have such a situation, these distributive laws are automatic. And we still observe that we have a special vector, the zero vector, which is just the empty M set. The vectors are M sets, so there's an empty M set. And that zero vector satisfies when we add it to anything, we get the anything. And when you multiply 0 times V in order to get 0. So it's an X, unlike 0 does. So it's very pleasant that these laws of arithmetic are almost automatic here. So when we set these up, they just fall nicely into place, and refreshing the work is required to understand and conclude. And there's also a distinguished special, a distinguished special, the special 0, 1, which officially is the M set, if it was just a singleton with whatever. And critically we call that D, P1, and now we see that it plays exactly the same role of alpha in the context of polynomials. So in other words, we can now introduce alpha in this Maxwell context by saying let's agree that this particular thing is alpha. In other words, we're defining E1 to be alpha. Well, then if you square it from here, you have to add 1 plus 1 to get the threshold, which has a single singleton of 2. Alpha cubed will be the singleton of 3, and so on. And so now we can write any vector V in terms of essentially 2 equivalent forms, in the form as a linear combination of E1, E2, up to Ek, as well as E0, or correspondingly in terms of powers of alpha. Alpha 0, alpha to 0, plus A1 alpha to the 1, plus A2 times alpha to the 2, so on up to say AK times alpha to the K, where we also introduce alpha to the 0 to mean this E0 vector here. So we have kind of linear algebra forms of U1 vectors. Sitting inside the same structure. And we use polynomial kinds of dimensions or thinking, and we use algebra types of thinking. We are getting this convergence of fundamental and high logic vectors and polynomials. They become essentially the same kinds of things. So this is a traditional vector, 31205, and now we know that relatively think about that probably in terms of a vector, that's a natural vector. That's what we as 3 plus alpha plus 2 alpha squared plus 5 alpha plus 4. Some vector, polynomial, some kind of vector there. And we realize that both of these objects are just manifestations of the underlying object, which is either this or a polynomial. But rather this underlying abstract. Okay, so underlying abstract is 3 zeros, that's number 1, number 2, 3, and 5.
担当者のインド天使は高橋車掌は移動です。
Interpretations of this object as a vector, or as a polynomial, or as a polynumber, or as something else, maybe a column vector rather than a row vector, for example. These are interpretations that we bring to this underlying object, which is just a data structure, a policy system. In the next video, we want to now connect more closely with the Hindu-Arabic story. How do Hindu-Arabic numbers, and the usual arithmetic that we're very familiar with, slot into this situation? We'll explain that next time. I'll just join you for that. I'm going to go over that sort of thing. Okay, I'm going over. We're having another look at it. And this turns out to be considerably more subtle than it's usually thought of, because we appreciate it now that huge complexity involved in larger and larger numbers. So the key insight that we have been developing. So we know now that just to hope that the kinds of experience and understanding that we have developed for smaller numbers, the hope that that extends in a natural way to all natural numbers is described. We have to think carefully on the scale at which we can legitimately and logically comprehend, define, and prove our arithmetic is valid. So the reality is probably that the currently regarded theory of natural numbers is too wide, it's too ambiguous, it's too all-embracing. We need to actually be a little bit more carefully in prescribing different aspects of the things which are now currently just clumped together. In particular, there's at least 3 notably distinct levels at which we can try to access what natural numbers are. The primitive natural number level, where we just regard a natural number as a set of marks, and we oblige ourselves to actually write down such as explicitly and completely in order to have the natural number. And that's a reasonable type between as a familiarity with numbers. And then there's the Arabic natural numbers, the most familiar ones, of course, where we write down something like this 3,793. And we're going to move to try to understand what that's all about in today's video. And we're going to try to move towards establishing some kind of definition for this other type of number. Distinguished from that. And the result of this level, which we're aware of, the arithmetic expressions for natural numbers, we were allowed to concoct expressions involving arithmetical operations, symbolized like this, or maybe more complicated ones like we can look at. And these are also candidates for numbers, but they're definitely different kinds of objects than these ones. And these ones are different kinds of objects than these ones. And they all have different sort of scales in which they're more appropriate. That's important thing to realize. That relatively small numbers are well captured with this, sort of medium kinds of numbers are captured with this, and very large numbers have to go to some system like this. It's like up there, and over here, kind of numbers. So we have a look at primitive natural numbers, and we see that they have a simple arithmetic, which is they're easy to understand, easy to compute with, and that even relatively small children can understand sort of why this kind of arithmetic may be of simple importance in that arithmetical logic does. When we go to Hindu-Arabic numbers, it's really a quite different story. Okay, so there's a very simple
Three
different ways of we have to say, of course, have to recognize that we are so familiar with the Hindu-Arabic system. I think we've been taught this system from a very early age. And we have spent hours and hours, hundreds of hours practicing, learning in the applications of this Hindu-Arabic system. So it's really almost hardwired into our mental frameworks. And we should take that for granted. Okay? It's actually not a replacement for a solid logical foundation for what actually these things are. So that's what we're looking for here. We all know that we can, do Hindu-Arabic arithmetic, at least for a relatively small number when the calculator is not needed. But what exactly is a Hindu-Arabic number? And what exactly are the definitions of addition, multiplication, and so on? And how do we actually prove the laws of arithmetic for these objects? That is what we're interested in here today. So our first approach to possibly setting up Hindu-Arabic numbers is to regard them as short forms for primitive natural numbers. That they provide us with a convenient way of concisely expressing these primitive natural numbers, which can be quite onerous to write down and express. So we use the primitive natural numbers and give them the usual names. So this one here, called 0, and we give it's the alternate symbol that we're familiar with. This thing here, the single market, number 1 with its usual number. This is 2, this is 3, and so on. This thing here would be 27. Okay, well, this is familiar with the system, but we know that it does take some explaining. To actually explain to somebody who didn't know what it was about. We have to talk about how we take one of these sets of marks and subdivide them into ones, tens, hundreds, thousands, and so on, and then count the numbers of those various things and string them together in our Arabic list. So you can proceed this way. This is a valid possible way of proceeding. Okay, that Hindu-Arabic number is just a short form for a primitive natural number. Then the definition of operations on Hindu-Arabic numbers simply reduces to those of the primitive natural numbers. This is a reflection of this prior arithmetic that we already had in place for the primitive natural numbers. So instead of saying 1 plus 1 equals 1, something like that, we might say 9 plus 13 equals 22. Okay, so it's a shorthand for it. So logically then, nothing really too much in addition is required. So if we just take this approach, then Hindu-Arabic arithmetic is completely equivalent logically to the arithmetic with natural numbers that we already have, the arithmetic with primitive natural numbers. And we apply this usage in the following way. So let's write on the phone that if we write 7 is of type NAT. Okay, what that means is that 7 is defined as this thing here. So this is the actual object in NAT. And when we write it, we agree that this here is defined to be this. This is a name for this. Okay, well, this is very short. Because there's a serious disadvantage with this. But it's a logical disadvantage that really only becomes apparent once we step outside the bounds of familiar, relatively small arithmetic. The disadvantage is that we are logically restricted to numbers less than 10 to the 200. Why? Because this is the maximum possible size of a primitive natural number in our universe. We've seen that if you want to write down a bunch of ones or marks, okay, the very, very most that you can do that is determined by how much room there is in the universe and how small you can write. And if you're writing a very small scale, just let's say a nice scale, and you're writing to fill the entire universe, so we decided that there's roughly 10 to the 200 such magnitudes filling our universe very roughly. Okay. And that's the upper bound for the number of marks that you can make. Of course, you can never make anywhere near that many marks, but at least in principle, we can contemplate something like up to that amount. Okay. But we are constrained roughly somewhere around this level. We are not able to conceptually even imagine in our universe n sets of stuff with a lot more than this number. For example, these various numbers that we call Z or Z prime or 3 star n squared 4. These numbers are so big that they completely overrun the possibility of actually exhibiting an m set with this number of objects in it. Okay, so that means that if we were to attach our Hindu-Arabic numbers to primitive natural numbers, we are constrained by whatever bounds we have on the primitive natural numbers, and we are constrained because the universe is probably always so big that we can less probably always so small. So let me illustrate this point by giving you an example of something that's arithmetically impossible for us, even though we actually want it to be possible. So consider the question of adding this natural number to 1. This is the natural number 96511. It's a natural number with roughly up to 200 digits. Therefore, this natural number is so big that it represents the size of a set, or a multi-set, which is impossible to conceive of in our universe. We cannot write down and exhibit, even theoretically, even in principle, an M set or a set which has this number of objects in it. So if we're thinking about this as representing a primitive natural number, we're just stepping beyond the bounds of what we actually can do. So we have to look at something like this and say, I'm sorry, this does not make any sense, because we cannot interpret this thing as a primitive natural number. But this is limiting for us. This is too limiting. We want to be able to make calculations like this, because we all could make this calculation like this. The end of doing this is just change that 3 to a 4. Our computers can deal with numbers which are this big. They can do all kinds of great computations with them. And if we're doing geometry in a integer framework, or rational number framework, once you go a few steps in complexity in some actual specific situation, you're actually making computations, then you should be surprised to have bigger and bigger numerators and denominators occurring. This is what happens. It's when you make addition of fractions or multiplication of fractions, then the denominators and the numerators are getting bigger. So every time you make a computation, then you're increasing sizes. And so it doesn't take that long before we can realistically end up with numerators and denominators that are of this order. So we want to be able to deal with them. We don't want to just throw up a hands and say, sorry, that's no longer supported by our theoretical constructs. So we want to do figure arithmetic, and so we need to free num from that. We do not want to identify these things. We do not want num to just be a replacement or a short form for that. That's too limiting. So notice how this understanding really does depend on our investigations of the numbers, and our investigation of complexity. We're thinking about complexity. We understand that there's limits out there in terms of how big you can write down expressions. And corresponding how big are the numbers that you have some realistic way of writing down some fraction or another. So we're trying to address that. We're not pretending that we're living in some unicorn inside the universe where there's a infinite amount of room that gives us things just by waving the hands around. We're not doing that. We want to really pin things down small and small. So what we want to do is we want to free them that number. Allow us to figure that is great. We want to understand more. So let's say as a separate line environment. Let's say what we're number as a separate system from that, but which correlates with it. So let's try to see some direction in which we could create a theory of natural numbers, Hindu-Arabic representation. Okay, so this is a lot more work. This is a lot fancier than dealing with natural numbers. It's several orders of magnitude more complicated than that. In fact, the has not yet been done. In 2016, there's no place where you can find a proper theory of Hindu-Arabic numbers. In particular, piano type fashion, some of you will have heard of an axiomatic approach to numbers. So the piano actually is still really complicated because piano is resting on the idea of building up natural numbers by successes. And if you want to start with one and then you add one, and then you add one, and then you add one, and you want to kind of build up an arithmetic, you're really essentially in the realm of primitive natural numbers. Okay, so piano is just an axiomatic approach to what we're calling natural numbers. In fact, it doesn't really aid us considerably. We'll talk about piano at some other point. In any case, piano is not going to help us going beyond the primitive natural numbers. We need to do something. We need to go beyond this. We need to have our numbers connected with an actual M set or a sequence of things that we can write down starting from one. Okay, so here's a rough outline of how to proceed. So here's a program that somebody is thinking very carefully about and work towards creating a theory of singularity numbers. It's remarkable that in 2016 such a program is possible. That this is a road that can be gone down by somebody who's careful and serious enough and really wants to do some work. To establish arithmetic, that's what we're talking about. It's not some tangential thing built on top of the strategies of the theory, built on the strategies of some other theory. Okay, this is core mathematics we are discussing here, isn't it? Okay, so how do we start? We can start by defining singularity numbers as expressions like this. Okay, that's not so hard to do. So a singularity number is an expression like this. What does that mean? Well, it's a list working like a string of digits. The digits are all taken from this set. The usual ones, 0 to 9. And the strings have the property that something are arbitrary, except for the rule that they can't begin with 0. They can't begin with 0, except for the trivial number 0 is 1. That's the only number that can start with the digit 0. I start out with natural, the digit 0. And all this must be non-empty without allowing any empty limits. So is a reasonable definition of what a singularity number is. Let's agree that you have a singularity number. It's like you can write down such a string. To write down a string like this one, you have a singularity number. So you don't need to suppose that there's some set somewhere that is counting. Okay, the singularity number is just this string that we write down. That is very sensible and concrete and reasonable way of defining between the two digits. Okay, so now we have the objects, the numbers themselves. We arrive to define operations. So segmentation, multiplication, let's see, what's our start? How are we going to define these? So note that now it's no longer possible for us to go back to the natural numbers. We can't say take your singularity number and find an M set or collection or set that has that many objects in it, and take your other singularity number and another M set that has that adds them together and count how many we have. Okay, that works only if we're in the realm of possibilities for exhibiting these M sets. And we've already flagged that we're going beyond that. Okay, so we cannot rely on converting our singularity numbers to natural numbers working there. But nevertheless, we can still connect with what we're doing with natural numbers. So we can create addition and multiplication tables. Okay, and so here's an addition table for just the digits themselves, and here's a multiplication table for the digits themselves. Well, the tables are not complete, but I'm sure you all can do them. Okay, so we're going to write down these tables. This is how we're going to define the addition of just our singularity numbers, which are given by single digits. So we want to know what is 2 plus 6. We want to know the table is obviously. We want to know what is 2 times 7. We want to know the table is 14. Okay, so of course this table doesn't tell us how to add more generally, but it's a start. Okay, so we give these tables and we define the operations on the single digits this way. And of course we all know that these things come from our understanding of natural numbers, primitive natural numbers, how addition and multiplication work for them. But in fact, we don't really need to say so. Okay, we can just say, here are 2 tables where we define addition and multiplication by these tables. That's how we tell our computer how to add digits, explain to the computer where we got these things from. Alright, so now the second part of that second step, we need to extend our understanding or definition of addition and multiplication to general singularity numbers. Okay, because we have lots of experience in primary school, we know in principle how this should proceed, roughly anyway. We know how to use those addition and multiplication tables to add and multiply more general numbers. We want to add 7, 3, 7, and 49. We know that we start on the right and we add 7 and 9 using the table. We get 16, we write the 6, we put the 1 up there. Then we add 3 and 4. We get 7, we add 1, we get 8. And then we bring the 2 down. So we multiply 2, 3, 7 by 4, 9. Well, we multiply 9 times 7 is 63. We write the 3, put the 6 up there. Then 9 times 3 is 27. We add the 6 is 33. Put the 3 down, put the 3 up there, etc. Alright, so the question of taking the familiar knowledge about how to actually add singularity numbers and telling our computer how to do that. That's essentially what the definition is. So extending our definition from pseudo digits operations to single string operations. So this is a fair amount of work, but it's not impossible. You can certainly program a computer to do this. And you can look at computers that have code that works selling on singularity numbers normally cancelable like this. And then we have other challenges. Disapprove the laws of arithmetic. This is more challenging than you might think. Because you are not allowed to use the prior knowledge of arithmetic with natural numbers, with primitive natural numbers. Okay, except for small numbers. So we can use the fact that for small numbers, 3 plus 7 plus 8 is the same as 3 plus 7 plus 8. So we can use those things, but we don't know that a social security law or a security is necessarily operating on these huge singularity numbers. Of course, we have to question that they will. Okay, not without argument saying, well, just convert these singularity numbers to their sets, and then we do the primitive natural number operation there. We know that these are fugitive, we're associated, we're fugitive there, and then we go back up. So the argument only holds up to the limits of our natural or primitive natural number system. Never proposing to go much beyond that. So we need separate, independent proofs of the laws of arithmetic. You can see that there's something together. It's actually a considerable amount of work, and it's not all just immediately obvious, but the most efficient and elegant way of doing this is. So a great math project, I think. I just think we need to spend a year or two thinking about how to do this really in a nice elegant way. It's very instructive. Okay, so we just write down this little broad outline here. We can put that together and then get a new system which we call singularity numbers, which extends the arithmetic of natural numbers and coincides with it when there's overlap. So you probably guessed that. That's not how we're going to proceed. We're going to proceed down a big different path. So this is the third approach that I want to suggest to you in terms of establishing arithmetic or invariant numbers. So I propose that invariant numbers can be viewed as multipliers. And when we take this m-set point of view, then we can exploit things that we already know, and we can create a alternate form of the particular invariant view. It will require us to think a little bit differently as we prepare to shift our orientation